Continuing this lecture on truth tables, we are going to look at putting together a complete truth table and determining the validity to arguments. So here we're putting everything together that we've been learning and actually utilizing truth tables for what they're helping us do, which ultimately is determining the validity of an argument. So remember, when we're dealing with arguments, we're trying to determine the truth of complex propositions, and complex propositions are put together from multiple simple propositions and then combined in a way using symbolic connective. So when we look at just simple propositions, these are, again, statements that could be true or false. Jamie went to the store, could be true, could be false. Aaron is acting very unusual today. Again, we're just stating one particular thing. There's not multiple parts to these particular sentences. Now, if we were to use a complex proposition, though, we would see that we would use one of those conjunctive, disjunctive, conditional statement, some sort of connective to connect multiple parts. So the stars and the moon will be visible during the day. This is a complex proposition because it's really making two different statements here. It's asserting that the stars will be visible during the day and that the moon will be visible during the day, and then putting them together to say the stars and the moon will be visible during the day. So now the truth of this complex proposition is dependent on the truth and falsity of the simple propositions that make it up. So in order for this to be true, seeing as that it's a conjunction, we would need to know that yes, the stars will be visible during the day, that is true, and yes, the moon will be visible during the day, that is true as well. So when both of those parts are true, the complex proposition is true. If either of those parts or both of those parts are false, then that complex proposition is false. Here we have more complex propositions. First, in the form of a conditional statement. If Trump gets his way, the US will no longer be part of the Paris Treaty in 2020. Again, the conditional statement being broken up into antecedent and consequent. So Trump gets his way is the antecedent, and then the US will no longer be part of the Paris Peace Treaty in 2020 is the consequent. So when the antecedent is true and the consequent is false, we know that that complex proposition is false. Any other combination of those simple propositions being true or false would make the complex proposition true. And then a biconditional, the MLS is only going to award a soccer team to San Diego if and only if San Diegans pass a stadium bill. So again, with biconditionals, we need both parts to be in agreement with one another. So they both need to be true or they both need to be false in this instance. So with each of the previous propositions, we can turn these into symbols, and then from those symbols, we can import them into a truth table. And then when we've completed the truth table, we can see the validity of a particular argument. We can see if the premises infer the conclusion, or rather, which we'll cover a little bit later, if the premises do not entail the conclusion. So it's time to focus on those truth tables in their whole. And so remember, there are keys for each of the 5 symbols that we've covered: the conjunction, the disjunction, the negation, the conditional, and the biconditional. Each one of these is going to help us fill out the truth table and combine simple propositions into more complex propositions. And then sometimes we will have these complex propositions that will make even more complex propositions. But we're always following this key, always doing the same things over and over again. So taking just a simple taking a single proposition, a complex conditional proposition, if John is not sick, then John is happy. Here we have 2 simple propositions: John is sick, John is happy. And we would symbolize this as follows: negation, skull and crossbones, arrow, smiley face. This is the symbol form for if John is not sick, John is happy. So the first thing we would do is to create our reference columns. And remember, reference columns are always going to be set up in the same way all the time. When we have two simple propositions, that means we know we're going to have 4 rows because there will be 4 combinations or 4 different states of affairs that can exist between these two simple propositions. One in which both propositions are true, one in which skull and crossbones is true and smiley face is false, one in which skull and crossbones is false and smiley face is true, and then one in which both skull and crossbones and smiley face are false. After that, we will create a column for each part of the complex proposition. So in order to determine the truth and falsity of this complex proposition, we need to know its parts. And so there is a negation skull and crossbones. We will take that first since the conditional arrow is the main connective. It's always going to be important to find that main connective. And so we need to do the skull and crossbones first. So going back to the negation key, we know that if the reference column is T, then our negation is going to be false. If the reference column is false, then we know the negation is going to be T. So here you see the skull and crossbones in the reference column on the far left, TTFF, which means that if we were to negate that column, we would get FFTT. Now that we have the negation skull and crossbones, we can rewrite the smiley face if it's helpful so that we can read from left to right, remembering that this negation skull and crossbones is going to be the antecedent and the smiley face is going to be the consequent. If we rewrite a column, we're just copying the reference column. There's no change to that whatsoever. I can write a smiley face column as many times as I want. It's always going to be the same. So here, I would look at negation skull and crossbones F and smiley face T and ask myself whether or not the antecedent being false and the consequent being true would make that complex proposition true or false. So now we would go to the conditional key and see the combinations for what makes that complex proposition true or false. For the conditional statement, we know that the only time a conditional statement is ever false is when the antecedent is true and the consequent is false. Now, in the 2 columns on the right, the only time that that is ever the case is in the 4th row. That means that the 4th row will be false for the complex proposition, and all the rest will be true. So here we have an even more complex proposition. We're going to do the same thing though. Here we have 3 simple propositions. The complex proposition as a whole being John is unhappy if and only if John is working and John is sick. Remember, 3 simple propositions. And so each one of those simple propositions is going to get a reference column, and those reference columns, again, set up the same way all the time. After that, we will break each simple proposition up into the next simplest proposition. So the next column will be a negation smiley face, since we need to know that negation smiley face before we can move on to anything else. And if we're negating the smiley face, we are simply just doing the opposite of what we find in the reference column. If the reference column is T, 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 F, 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 we know that the negation smiley face will be F, 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 T, 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 T. And then the next simplest proposition of the complex propositions is the conjunction. Knowing that the biconditional double-sided arrow is going to be the main component because it falls outside of those parentheses. We know when we see parentheses, we have to do what's in the parentheses before we do anything else. So here, remember, a conjunction is true only if what's on both sides is true. So we go back to the reference columns. Here we're looking at column 2 and column 3, the column with the computer screen and the column with the skull and crossbones. We know that when we get T and T, the complex proposition will be T. Any other combination, we know that the complex proposition will be false. So here we can see that in row 1 and row 5, we have truths, and all the other rows are Fs. Once we're done with this, we can combine these two parts, the negation smiley face and the computer screen and skull and crossbones, using the major connective, which is the biconditional. And from that major connective, we can then form the truth of this complex proposition as a whole. So remember what's on both sides of the biconditional. If they are both true, then the complex proposition is true. If they are both false, the complex proposition is true. It's only when they're different that it becomes false. So here we can see in row 1, 6, 7, and 8, they are different, so they will be false. In row 2, 3, 4, and 5, they are the same, so those are going to be true. Now, when we're creating the completed truth table, we're doing the same exact thing, only we're incorporating all of the propositions, the premises, and the conclusion into our truth table. So we will create columns for each one of the premises and for the conclusion. And then from there, we will be able to see if the premises do not entail the conclusion. So if this is the argument, negation, skull, and crossbones, if negation, skull, and crossbones, then smiley face, negation, smiley face, therefore skull and crossbones. We can create a truth table by creating reference columns first. We see that there are two pictures represented, which means two simple propositions, which means 4 rows in our truth table. So we have our reference columns. We then will start breaking everything up into the smallest parts. So we need to do negation, skull, and crossbones first. We're just negating column 1. And then after that, we are going to rewrite smiley face just so we remember what's the antecedent and what's the consequent. If you don't want to write the smiley face column because it's already written, that's perfectly fine, but it always is helpful to read from left to right, noting that your column on the left will be the antecedent and the column on the right the consequent. So here, again, we're looking for a true antecedent and a false consequent, which we find in row 4. So we know that row 4 is going to be false. All the others are going to be true. And then this is a premise, so I've labeled it blue, or I've colored it blue so that we know for later. The next premise is negation smiley face, so we're just going to negate the smiley face reference column and get the opposite. If the smiley face column is true, false, then the negated smiley face will be false, true. And then lastly, we will rewrite the conclusion here in green, and we're just copying over the reference column because it's just a simple proposition here. So here we can see the premises in blue, and we can see the conclusion in green. And this is the completed truth table. This is all you need to do. It's simply just following the keys, following the rules, knowing where to put T's and where to put F's based on the keys that started this lecture and that finished up the lecture previously. Now, when it comes to testing for validity, remember, a valid argument is an argument in which the premises infer the conclusion. The conclusion is forced by the premises. So when we're determining the validity of an argument by looking at a truth table, we are looking for a combination in which the premises are true, but the conclusion is false. If we can find a combination where the premises are true and the conclusion is false, then we know that the premises have not inferred the conclusion, which would render the argument invalid. And so if this happens in any of the rows, it is going to be an invalid argument. This is kind of like how math works. Imagine the different rows being different dream states that you would be in. Well, even if you were in a dream state, while the laws of physics might be different, I might be able to fly in a dream or being chased by zombies in a dream, 2 plus 2 is always still going to equal 4 in my dreams, and it's going to equal 4 in real life. So in each state of affairs, I know that 2 plus 2 equals 4 because this is a valid argument, essentially. And so when it comes to our arguments, even though we have all these rows of states of affairs, if in any row the premises fail to lead to the conclusion, then the whole argument is going to be incorrect or is going to be invalid. This is the only combination we are looking for, true premises and a false conclusion. If we have true premises and a true conclusion, that doesn't really tell us anything. If there's a false in the premises and a true or false in the conclusion, that doesn't tell us anything either. We're only looking for true premises and a false conclusion. If we find that in any row, the argument is invalid. If we do not find that in any row, or if there are no instances where there are true premises and a false conclusion, then the argument is valid. So when we look back at this argument, are there any instances where we have true premises and a false conclusion? Well, the only row where we have true premises is in row 2. However, the conclusion is true as well. So this doesn't tell us that it's invalid, which means it is valid. So truth tables are essentially trying to falsify an argument. So let's take another. If John is sick and flying, then John is not happy. John is sick, John is not flying, therefore John is happy. We have 3 simple propositions, and we would rewrite this in a symbol form as if parentheses P and Q, then not R. P, not Q, therefore R. So our argument in symbol form, we know that there are 3 components, 3 simple propositions, which means we're going to have 8 rows, which means our reference columns are going to be set up like this. Always the same all the time. Reference columns never change. Then we will start breaking it up into its simple parts, P and Q. Remember, just following the key of the conjunction. When P is true and Q is true, then P and Q is true. If either of them or both of them is false, then it is false. Next, we'll do not R. The negation is just the opposite of the reference column. And now that we have both of these, we can do the conditional statement. And then each of the other premises are simple enough that we can write them down. And then finally, we have a conclusion. So with our completed truth table, we now want to look and see if there are any instances where we have true premises and a false conclusion. Here, it seems as though in row, let's see, 1, 2, 3, 4, in row 4, we have true premises and a false conclusion. Because we have this combination, the argument is invalid. This is all we have to do now. Just simply write invalid, and we know that this argument is not a valid argument because there is a state of affairs where the premises do not lead to the conclusion. And if there's even one instance where premises don't lead to the conclusion, then this argument is not logically structured. Lastly, it's important to just recognize certain types of aspects to really just reforming arguments in their structure. We're going to look at this more in depth later on in the semester, but an example that could help, De Morgan's law, basically just expresses how to distribute a negation. And so if we're ever looking at negation, parentheses, P and Q, we would simply write this. The equivalent would be negation P, disjunction, negation Q, and then vice versa here. So in certain instances, if we're trying to break up complex propositions into simpler propositions and we're not quite sure how to create the columns, we can distribute the negation and make columns for pieces without parentheses, essentially. So if you're having trouble coming up with a column with parentheses in it, we can always break those pieces up into simpler parts. But when we do that, we must note that there are certain aspects that are equivalent to others, and that we can't just take out the parentheses and expect the complex proposition to work the same.